you make anything interesting in the shop recently, Professor McDonald?
Okay, welcome to class. I guess hope everybody can hear me. We're going to do mostly lecture this today on Thursday, and we'll be completing my coverage of the material around ocean circulation, which I believe is chapter 9 in Garrison. And you recall on Tuesday we left off with a discussion of surface currents, and we introduced the concept of gyres. And these are large masses of rotating water, huge masses of rotating water, thousands of kilometers across, that occur in each of the major ocean basins. And because of the effects of the Coriolis effect, because of the influence of the Coriolis effect, and because of the influence of the major wind patterns, these gyres tend to be situated in the western edges of the major ocean basins and to have a western intensification. So I'm going to now explain a little bit how that comes about. However, I would be remiss, I think, given the news today, if we didn't go back and look a little bit at the wind patterns that we're experiencing and discuss how the prevailing winds, Coriolis effect, are producing the what's called the polar vortex, which is wreaking so much havoc. It's created a weather effect that's really disrupting life, certainly in Texas and elsewhere in the country. So you'll recall this picture of that we showed in the discussion of atmospheric circulation last week. And during that discussion, we talked about these different cells of convection cells, and I've reiterated that on a number of occasions. But the one I want to focus on is this polar cell. Okay, so we kind of have the concept now of convection currents rising in heat and sinking patterns of air, and how they set in motion surface winds and high altitude winds. Well, we focused mostly on the Hadley cells with the production of warm, buoyant air around the intertropical convergence zone. And we talked about that and how they give rise to the trade winds, these west to easterly flowing winds. And we talked a little bit on Tuesday about how the pattern of these winds creates a westerly flow in surface currents. A lot more about that in today's lecture. But the situation in the polar cells and the behavior of the polar cells recently is different, in that the major impetus is not rising air due to warming of the planet around the equator, but sinking air because of the cold conditions that prevail in the high latitudes. So both at the North Pole and the Southern Pole, you have the coldest air, which at the northernmost or southernmost extreme. So that air is sinking, and with that sinking air, there's a movement of high altitude wind, which moves to replace that air that sinks. This is kind of familiar to you. We've got this pattern here. Okay, so the movement of this air from south to north is going to produce a rightward deflection of air movement. And that rightward deflection here would be a west to east flow. And this west to east flow is what's known as the jet stream. So there's this jet stream which occurs in high altitude air movement around at the border between the Ferrel cells and the polar cells, around 60 degrees north latitude and 60 degrees south latitude. In both cases, the weather pattern is from west to east. Okay, and with that motion, the pattern isn't circular, but it tends to form waves. And typically there are 7 waves that occur around the planet from west to east. And so these waves are deflections of the jet stream. Okay, so that's what's depicted here. In the stable polar vortex, you have a strong jet stream flowing from west to east. And if any of you have flown from the United States to Europe or back again, you will have noticed that the trip, and actually from coast to coast, the trip from the west coast to the east coast typically takes, a half an hour to 20 minutes less than the trip in the opposite direction. And that's because when airplanes are flying, they get up into the layer of this jet stream, and they can ride these strong jet stream currents from west to east, but going the other way, they have to fight them. Okay, so this is a strong jet stream, and this is the prevailing condition. This is what we'd expect to see. Well, we also know that there has been in a condition of global warming due to climate change, and that global warming has produced unusual warm temperatures in the high latitude regions. So for the last several years, the polar regions, the north polar region, has been warming, and it's warming at a rate of about 2 to even 3 times faster than warming has taken place in the more temperate regions where we live. Okay, so if that warm air or if that warm trend prevails, what's going to happen to that sinking air that we described occurring at the northernmost extent of the polar cells? Remember that? So this air is sinking here, and it's sinking due to its extreme cold. Okay, well, if it's not as cold, that air is not going to sink as rapidly, and the polar vortex will tend to slow down. And with this slowing of the polar vortex, the jet stream develops these deep meanders. So these are the meanders of the jet stream, and they're typically, as I said, 7 that occur around the planet. Well, with the weakening, these meanders become, the amplitude of these jet stream waves becomes steeper and steeper. So the cold air moves south, and with that southern motion, you can have extreme cold events that dip down pretty far south. And that's what's happening now in Texas. And that weather pattern, so that the meanders in the jet stream, the so-called polar vortex, descends into much more southern regions than is normal. It's hard to know what's normal these days, but which has been historic. And so you were getting these weather patterns. And interestingly enough, I looked through my notes and I gave us a similar lecture last year. And last year at this time, there was a major polar vortex, an unusual weather pattern taking place right around February or March when I was lecturing on this same pattern. It wasn't as severe, didn't produce the really terrible, catastrophic sort of cold snap that's impacting Texas right now, but nonetheless, it produced very, very frigid temperatures. And so there's a real sort of reverse of the normal arrangement of temperatures from south to north. So that last week, Minneapolis had temperatures below 0 Fahrenheit, while Fairbanks and Barrow, Alaska had temperatures in the 20s. Which I guess is considered fairly warm for that part of the world at this time of year. So here we can see a real-world example of many of the things that we've talked about: the formation of these convection cells, the way in which these convection cells create a pattern of wind, both at the surface winds and the high altitude winds, and the way in which the changes in the sort of normal distribution of temperatures and circulation of temperature across the planet is producing unusual weather patterns. And we should anticipate, I say we, the citizenry of the world, should anticipate that as global warming continues, and as it continues particularly intensely in the high latitude regions, so the polar regions are warming much more rapidly than the southern regions, that this sort of unstable condition, these unusual weather patterns, will occur more and more often. And that's exactly what's happening now in Texas. And so, part of the problem in Texas is that they've had these unusually cold winter storms, and with below freezing temperatures, snow even, snow in Corpus Christi, which is pretty far south and is really not equipped for that. So that's one problem. But the other problem was that the authorities in Texas didn't anticipate that there would be such a severe set of weather conditions, and they failed to winterize the power grid and the power generation capabilities, so that when this storm shut everything down, and then the state, the grid, the power distribution grid in Texas is independent of the power distribution grid across much of the other US states. And so Texas wanted to isolate their power grid from the national power grid in order to avoid federal regulation of the power grid, or so I've read. And as a consequence of that, they are kind of cut off, and they can't import power from the rest of the grid because the grid literally isn't corrected. The Texas grid literally is not connected to the grid in Arkansas or Louisiana, where they have more power capabilities. So there's been a sort of a cascade of unfortunate effects, but the main driver of that cascade is this extreme weather conditions produced ironically by global warming. So global warming is giving Texas intense cold right now, and hopefully it'll move through and they'll get things back together. But this is a very severe impact, and these kinds of impacts of climate change should be anticipated. And the adaptation to climate change is going to cost a lot of money as we adapt the infrastructure to conditions which we can foresee. And so I don't want to get too political, but the ability of the citizenry and the government to make these sort of changes is going to be a major source of contention and political conflict, I think, in the months and years to come. And the way in which it's resolved, both nationally and regionally, is going to have a lot of impact on people's quality of life. So that's my point of view. Okay, so let's move on from atmospheric circulation. Any questions about that before I go on? Any questions? Joseph, go ahead.
So that's why you see the big V shape in the temperature maps, is because of the meanders of the jet streams.
Yeah.
Okay.
Yeah. So the jet stream meanders, and as it meanders, it allows so that strong jet stream and around there is sort of a barrier to keep the polar conditions up north. And as that decays, and as you get this jet stream sort of meandering like this, it's as if you open the fence a little bit and allow these colder temperatures to descend further north than they otherwise would do. Okay, there's a lot more complexity to it than that, and I'm presenting a simplistic view of this, but fundamentally that is what's happening. Okay, any other questions? All right, well, let me move along to another sort of circulation pattern, and that's oceanic dryers. And let's see, where are we? Yeah, so we talked about the fact that the trade winds, the prevailing westerly winds, tend to push water from toward the western side of the Atlantic. And let's focus on the Atlantic for the moment. It turns out that the Earth is rotating eastward, and the winds tend to push things to the west, and that's sort of a global pattern, and we can see that everywhere. So in the Western Atlantic, there's this mound, and I use the word, as I said on Tuesday, I used that word advisedly because you wouldn't be able to register this mound at all if you were standing in a parking lot or anywhere. You couldn't see it, so it has a total relief of maybe 20 centimeters or 30 centimeters across an extent of several thousand, diameter of several thousand kilometers. But nonetheless, gravity sets water in motion as it tries to correct this. And what this produces are narrow, deep, warm, strong currents that flow from south to north in the northern hemisphere. And an example of this is the Gulf Stream. Well, that gyre, that circulatory pattern, comes back the other way in what's called the Canary Current. And that Canary Current is broad, shallow, cold. So this is a typical flow within a gyre, and it pertains no matter where you are on the planet, that there's this sort of western intensification. So let's try to understand that in a little greater clarity. So the gyres occur in the north and south and the Pacific, and they have this general formation. The western leg of the currents in both hemispheres tends to be warmer, deeper, and stronger than the eastern leg. So that's something you can put in the bank and count on. And that's exactly the sort of thing that I tend to ask on exams. So in an exam, I might ask you to draw a diagram of the North Atlantic gyre and describe the current patterns in different regions of that gyre. That's a typical question that I tend to put on midterms because it requires students to show their knowledge of these basic processes. Okay. All right, well, let's examine that a little bit more closely. So we've talked about this flow here, and we've talked about sort of the general trends that describe this, but there's something deeper going on, pun intended, and that is the role of vorticity in what we call Western intensification. So the term Western intensification refers to the fact that in the western regions of ocean basins, you tend to have these warm, deep, strong, northward going or pole, latitude, from low latitudes to high latitude currents. And then the return currents tend to be broad and cold and less strong. Okay. So why does that occur? Well, yeah, so these are the western boundary currents. So this is the general pattern with this strong Gulf Stream. So the water comes in, and in the Gulf of Mexico, this pattern is called the loop current. And then the loop current whips around, comes in and forms a loop is extreme here. The actual variation in the depth of the loop current varies from month to month and from year to year. But fundamentally, the water is flowing from the northern central portion of the Gulf around the Straits of Florida and where it joins into this Gulf Stream. It's called the Gulf Stream for a reason, because it has this origin in the Gulf, namely the Gulf of Mexico. Okay? And so the key to understanding this pattern of strong western currents, strong warm western currents, and deep cooler eastern currents is something called vorticity. Okay, so vorticity is similar to the Coriolis effect. It's mathematically identical. It goes to a maximum at the poles and zero at the equator. But vorticity is caused not by acceleration, but by deceleration. So if you have, let's see, let me switch to the next current. So there's, this is showing that there's large positive vorticity at the higher latitudes, and it goes towards zero at the lower latitudes. Well, what's causing that? We can understand positive and negative vorticity tend to balance, and this produces western intensification. So as water is flowing northward from the Gulf and forming the Gulf Stream, there's an acceleration as you move away from the western, from the eastern coast of North America. And this is kind of easy to understand. So there's as the currents are flowing along this continental barrier, they tend to be slowed by friction with the land. Therefore, as you move from near shore to offshore, there's a relative acceleration. Okay, there's a gain in positive vorticity. And so in a way, the water is moving more rapidly as you go offshore. Okay, so you can imagine that the current would go to zero at the coast because there'd be maximum friction, and also there's this barrier. Water can't continue to flow on land, so the flow is trapped against the eastern coast of North America. And as you move westward, and the current is allowed to flow more rapidly. Well, that flow that is experienced as an acceleration, and just like any acceleration in the northern hemisphere, it produces a rightward intensification, a rightward deflection. And so that's basically what you're seeing. So there's a rightward deflection of this intensified current as we move offshore. Let me stop there and ask if everybody got that. Do I need to go over this again or explain this in more detail? So we understand that any kind of flow or any kind of acceleration is going to have a, let's see, any kind of flow is going to experience a deflection due to Coriolis, and that deflection is going to be greatest in the higher latitudes. Okay, so we've got this north-going flow, and the flow is going to be deflected, and that intensity of deflection is going to increase as the water moves northward, because Coriolis increases as a function of the sign of the latitude. Okay. And then, the wind continues to supply, and there's a return here. And as it returns, the same sort of gain in positive relative vorticity occurs as water is interacting with the European continent. And but this, this general gain changes so that the gain decreases, the deflection decreases as you move further south. And so this pattern, more intense Coriolis deflection moving northward, less intense Coriolis deflection moving southward. And so that produces this broad, more surface-directed current in the eastern side of the North Atlantic. Okay. It's also colder because the water which is set in motion is sourced from higher latitudes, and it's intrinsically colder. It's less heated. Okay, and so this is a typical shape for a gyre. And we can see the Western Atlantic gyre here drawn out. So there's this loop current. You've got an equatorial current which is flowing in through the Straits of Yucatan, and then it makes this loop in the Gulf of Mexico and then flows northward, forming the Gulf Stream off the east coast of the US. This is this narrow, warm, deep, strong current, and it becomes more intense as it moves northward, starts to spread out and deflect around, and becomes this, describing this circulatory pattern of the subtropical gyre. All right. Show this in a number of different ways. Gulf Stream moving north, Canary current moving south, north equatorial current flowing in through the Gulf. You can draw this in a number of different ways, but I really want you to take away this message, this sort of picture of how a gyre works, and use the North Atlantic gyre as an example of that. We'll be asking questions around this. There were questions around this in your reading quiz, and this is certainly going to appear on the exam. So really try to gain an understanding of this so that you'll be able to explain it in a cognitive way when it's asked. So that's the North Atlantic gyre. And it turns out that all across the globe, because of the way that the Coriolis effect is oriented, that this western intensification occurs in all the ocean basins. So here are the gyres, the geostrophic gyres within the world ocean. So you have, in the South Atlantic, the current is reversed, so it's going from north to south, Okay, but in the southern hemisphere, Coriolis has a leftward deflection. So that's producing that, and that moves southward and then comes back in this Begala current. So North Gulf Stream giving way to the Canary Current, and the Brazil Current giving way to the Bengala Current. How many people, and you can raise your hand or make some other symbol, how many people saw the movie Finding Dory? Yes, many people. Okay, do you remember how Dory, or Dory's father, forget his name, what was Dory's father's name? The little clownfish who goes on the great adventure to save his offspring. Do you remember how he gets from the tropical region where he is captured, where his child is captured, where Dory is captured, and Finding Nemo, I'm sorry, Dory is the, I can't get my characters right. Dory is the other fish that helps out the clownfish, and Nemo is the lost clownfish. Okay, well, if you'll recall, they get caught up in the East Australian Current, right? And the East Australian Current is this strong current that's flowing from north to south along the east coast of Australia. So this is the same idea. And it carries them down to Sydney down here, where they're able to rescue Nemo from the pet shop where he's ended up. Remember that? So the East Australian Current, if you're trying to come up with another example of a Western intensified current, is another example of this sort of Western intensification. Okay, so that's a bit about these large current patterns. And I want to talk about some more aspects here. But before I do, I want to just touch briefly on the technology that's involved. I'm talking about measuring currents and how do we measure currents. Well, you want to measure currents, and the ability to measure currents is a relatively new technology. It's been around for only 100 years or so. And the old style current meters, and I'm old enough to remember deploying these old style current meters, and they were a major pain in the neck. They were heavy, and you had these directional vanes. So this thing would be hung on a cable. And there'd be a directional vane which would sort of keep the paddle wheel oriented into the oncoming current, and it would spin, and there'd be a dial counter which would count the number of revolutions between the start and the stop time. And so these things would be deployed, and there would be hundreds of thousands of revolutions, but by knowing what they were, and by measuring these changes at regular intervals, it was possible to deduce what the current had been in this local area. So that's how we used to measure currents. Nowadays, nobody does that anymore. I don't think there are any actual current meters outside of museums deployed anywhere. Current meters like this. Nowadays, the measurement of current is done acoustically using something called an acoustic Doppler current profiler. And the way an acoustic Doppler current profiler works is that there are a series of transducers, in this case 3. They also have ADCPs that are built with 4 transducers. But fundamentally what's happening is that there is a sound pulse sent out from each of these transducers, and then the instrument listens for reflections back to the transducer. So it sends out a ping, and then the ping, the sonic energy, is reflected back to the sensor according to small particles in the water column. So bits of plankton, marine snow, sediment even, reflect some of that energy back, and that return time, just like we saw with the depth profiler, allows a sort of measurement of time. Well, by comparing the arrival time amongst a series of transducers, it's possible to deduce the difference in flow or the differential flow between the different transducers. And so that builds up a pattern of the water flow. And the great thing about the ADCP is that it integrates the return signal, not just from a single particle floating in the water, but from multiple particles floating in the water, so that ADCPs can produce a profile of ocean currents that, depending on the frequency, higher frequency ADCPs produce higher resolution but lower range. So a surface ADCP might have a range of 100 meters, whereas a low frequency ADCP might have a range of 1,000 meters, but do so with less distance. And so this is what you get. ADCP data produces profiles of water flow. And what the modern system does is it relies on a network of buoys that are reporting in real time. So here is the depth profile. This is the along, and this is broken up into two components. There's a long shelf current and a cross shelf component. And these two vectors can be combined to indicate the net flow of water. So in this diagram, and this is time on the x-axis and depth on the y-axis. So there's typically this would either be sitting on the bottom looking up or hanging from a buoy looking down. In either case, you get this profile, and you can see from this diagram that there was a relatively strong flow in the positive direction during this period of time, and relatively weak during in the cross shelf component. And then this changes, it switches around so that there's different directions. So that by combining the along shelf component and the cross shelf component, you would get net vectors of current transport. But typically, when you see an ADC profile, this is what you're looking at. Okay. All right. Well, that was a brief excursion to look at how we measure these currents. And the measurement of currents is, by now, it's a huge enterprise. There are current meters all around the globe, and many of these current meters are attended remotely. They work robotically. Woods Hole has a series of current meters that are deployed in all the oceans, tens of thousands of miles away, and they control and collect data from these with robots and autonomous gliders and drifters. So it's a big enterprise, but it's what allows us to have a picture of the way that ocean movement is flowing around the planet, and not just a theoretical, but a real-time example, and sort of seeing how current flow, measured current flow, corresponds to theoretic current flow is one of the things that allows oceanographers to consider changes, and seasonal changes, regional changes, climatic changes over time. Well, let me talk a little bit more about vorticity. I think this is a diagram. Yes, here we go. We've got a video here, and we're going to consider vorticity in a number of different ways. Let's see.
Isn't it wonderful that we can flush a toilet and call it science? This video was shot in the Northern Hemisphere. There is much confusion that the rotation of draining water is related to the Coriolis force, or if other forces cause the water to rotate in a specific direction. The Coriolis force is a force that is a result of the Earth's rotation. The Earth's rotation deflects moving objects. If the Coriolis force is the primary effect, then the water will drain counterclockwise in the Northern Hemisphere and clockwise in the Southern Hemisphere. For this experiment, all we need is a drain, water, and maybe food coloring. The food coloring makes it easier to see the rotation of the water. The toilet water goes down counterclockwise. This wash tub has a faucet that can fill the tub from the left or the right. The faucet is positioned to fill from the left side. The water is making a counterclockwise rotation as the tub is being filled. The tub is filled, and the drain is pulled. The water is draining counterclockwise. Now the faucet is moved to fill from the right side. The water is making a clockwise rotation as the tub is being filled. The tub is filled and the drain is pulled. The water is draining clockwise. This sink's faucet is fixed and filled from the middle. The drain is open. The water drains counterclockwise. The sink is filled again. This time, the water is stirred very lightly in the clockwise direction. The drain is opened. The water drains in a clockwise direction. The sink is filled again. The water is stopped and allowed to sit for 15 minutes. The drain is open. The water drains without any rotation. Feel free to place your own findings in the comment section on which direction the water drains for you and which hemisphere you're in.
Okay, so that was a little amusing diagram, but you can certainly imagine a multiple choice question on an exam saying that the rotation of water draining from a sink is a result of A, Coriolis effect, B, the temperature of the water, C, the depth of the basin, or D, vorticity. And what would the correct answer be?
D.
D, very good. All right, so keep that in mind. And that's a common misperception that somehow the toilets will flush in a clockwise direction in Australia. Not true. Although I've never been to Australia, and so I can't verify that, but that's a way that people would misunderstand the difference between vorticity and the Coriolis effect. Okay, a little bit more. Let's take this concept of rotating water masses and the consequence of rotating water masses and try to explore some other examples. So we've talked about these flows of water, and so let's look at a western boundary current, the western boundary, and so here's the Gulf Stream flowing along the east coast of the U.S. And so as it moves, it's interacting with cold coastal water. And so there's a sort of a counterflow or shear along this, this boundary of the warm water flowing from the Gulf Stream and colder coastal water influenced by colder water from further north. Well, as these two water masses move past each other, you get this sort of wavy pattern where there are waves in the generated by this interface between water masses moving in different directions. So as these waves increase in amplitude, what the tendency is to pinch off gyres or eddies of, so these are smaller scale. So what we call a gyre is a large scale feature and an eddy is a smaller scale feature. So you tend to pinch off eddies, and these are rotating masses of water, and these eddies can migrate. So if you pinched off a bit of the Gulf Stream and moved it into the colder coastal water, you'd have a cell of warm water surrounded by colder water. And okay, so if there's a cell of warm water surrounded by colder water, that warm water is going to be higher in the middle, right? It's going to be warmer, so there's going to be a slight doming of that water because the water tends to expand with temperature. Well, the warmer water, the dome in the center of the warm chord eddy, is going to try to flow outward to adjust that gradient, barotropic gradient. And as it does so, the Coriolis effect is going to deflect it to the right. So you're going to get a clockwise flowing warm chord eddy. The opposite occurs if you pinch off a mass of this cold coastal water and surround it with the warm Gulf Stream water. Then you have a cold chord eddy. In a cold chord eddy, the center of the eddy is lower than the surrounding water because it's colder. And so there's a flow toward the center. That's one thing that's happening, and there are also vorticity effects that are present. So there's a conservation of vorticity that occurs in the southern, in the cold water and the warm water. So these two processes together produce these rotating gyres, and these rotating eddies rather. And these rotating eddies turn out to have not just consequences for oceanography and for navigation, but they also have biological implications, because the warm water flowing in the Gulf Stream is nutrient poor and tends to be less productive, tends to have less plankton, less primary production, fewer fish, etc. So this warm chord eddy would tend to have lower concentrations of marine life than the cold chord eddies. And so you can actually, oceanographers would take plankton samples moving across one of these warm chord eddies, and the abundance of plankton and other marine organisms would be high in the surrounding waters and low in the warm chord eddy. The opposite is true in the Gulf Stream. So there'd be a cold chord eddy, which would have relatively higher productivity. And so if you were taking plankton samples on a transect across one of these eddies in the Gulf Stream, you would find low plankton, high plankton, low plankton as you moved across the eddy. And this is something that is a measurable effect. You could also measure the change in temperature to register that one of these eddies have been crossed. Okay, so here we've been spinning around in clockwise or counterclockwise direction in response to Coriolis, in response to vorticity, current shear, and many processes. And the mathematics and the formal derivation of these things is a high order problem, but the basic concepts, I think, can be expressed in this by looking at these things in terms of vectors, in terms of arrows showing the direction of flow and the intensity of flow. And so by looking at these vectors and by trying to understand these diagrams of flow, I think we can get a pretty firm grip on what's with the general principles that are happening here. Okay. All right, well, let's one more example of that. So eddy formation. The other thing that can occur is the other thing that can produce flow is what's called convergence and downvergence, or convergence and divergence. Excuse me. So if you have so let's imagine that we've pinched off a bit of the warm water from the Gulf Stream. And so you've got this eddy here, and there's a current, geostrophic current, a current generated by the topography of this eddy, and it flows outwards. Okay, so as this water flows outwards, surface layer sinks, and there's a convergence in the deeper water layers. So the conversion is a convergence zone below the warm chord eddy. Water is flowing outward. To replace this water flowing outward, there's a convergence of water from either side. Likewise, if you have and perhaps more important, if you have a cold chord eddy, the surface layer thins, there's flow outward. To replace this flow, you get upwelling. So the upwelling in divergence zones can be very important in terms of its impact on productivity. Productivity in the ocean very much depends on the availability of nutrients. We're going to talk more about that after the midterm when we get into the living ocean processes. But typically, there is when you have an upwelling, you're bringing nutrient-rich water from deeper zones up into the surface. So where there's divergence, and processes which produce divergence are going to produce upwelling. And upwelling can be biologically important because it provides plankton living in the surface of the ocean with nutrients that tend to sink and be trapped in deeper layers. So this divergence-driven upwelling is an important process. And downwelling. Okay. And let's see. On a large scale, this upwelling and downwelling process occurs particularly importantly across the equatorial regions. All right, so this requires a bit of, combining different ideas. So we have, here we're showing the Pacific Ocean, and we're showing the location of the intertropical convergence zone across the Pacific Ocean. So that's shown in temperatures here, warm temperature. Well, we know that there are surface winds, trade winds that are flowing south across this region. So there are winds that blow diagonally across these surface waters. Okay, well, so here's the equator right here. And what happens when, to the Coriolis effect, when you approach the equator?
It weakens.
It weakens. In fact, Coriolis goes to 0 at the equator. All right, well, let's think about that process. So we've got a rightward deflection in the northern hemisphere, a leftward deflection in the southern hemisphere as this wind flows across the ocean. And then, of course, the Coriolis and the Ekman processes are causing the wind to move at the water to move at right angles from the wind. But that effect goes to 0 at the equator because the Coriolis effect goes to 0 at the equator. So that means that the displacement of water, the deflection of water to the right at right angles to the wind, is more intense on either side of the equator than it is at the equator itself. Okay? So that means that there's a divergence as you water relative to the equator. So you've got this geographic equator, in this case a southeast trade wind. It's blowing across this equator. In the southern hemisphere, the water is directed to the left. In the northern hemisphere, the water is directed to the right. So there's a left deflection and a right deflection at right angles to the direction of the wind, which goes to 0 at the equator. And so it increases as you move away from the equator. Well, if you have that on either side of a 0 motion, what that is divergence across the geographic equator. So if we recall what divergence did, remember in our previous slide, we said if there's divergence, so water moving away from some region, there has to be a replacement from deeper water. So you get equatorial upwelling as a result of winds blowing across the equator. And this equatorial upwelling is particularly important in the Central Pacific region, Central Equatorial Pacific, where the amount of nutrients, the presence of nutrients tends to be very low. So you get a band of high productivity along the equator as a result of water upwelling to replace this divergent surface flow near the equator. And that upwelling water brings with it nutrients, and so you get a region of high productivity along the equator, and this region of high productivity is particularly prominent in the equatorial Pacific. Right? So, and we'll see that when we start looking at the distribution of primary productivity in the world's oceans. You'll notice that there's going to be a pattern of high productivity in the central equatorial Pacific region, also in the equatorial Atlantic region and Indian Ocean as well. So this is driven by this pattern of divergent upwelling and downwelling. Well, so that's one form of upwelling and downwelling. Probably receives more attention, or more, you may have come across it more, are what is examples of coastal upwelling and downwelling. So here. So upwelling is wind-induced vertical circulation. Upwelling is upward motion of water. Downwelling is downward motion of water. And upwelling is important because it brings cold, nutrient-rich water to the surface. And downwelling is important because it supplies the deeper ocean with dissolved gases, particularly oxygen. Well, where would we get coastal upwelling and downwelling? Well, let's consider the coast of see, this is the coast of this is the coast of South America. And in South America, there's a wind from the south that blows along that tends to move along the Pacific coast of Chile, Argentina, and Ecuador, particularly Peru and Chile. Okay, so there's a strong wind from the south, all right. I'm sorry, wind from the north in the blowing this way, this direction. Get myself oriented correctly. Let me restart that comment. So here we have the coast of Peru, the Andes Mountains, and there's a seasonally strong wind that blows south along the coast there. Well, with that wind going to the south, there's water is driven offshore, and so the water is carried offshore to the left of that motion, and with the divergence, water has to replace that movement by upwelling from depth. So there's particularly intense upwelling, wind-driven upwelling along the coast of South America. And there's also similar upwelling along the coast of California, generated by different sorts of wind patterns. So Okay, so upwelling, here's the picture here. Upwelling provides, offshore Peru provides nutrients for plankton and fish. So they're very important fisheries along this Peruvian coast. And so here's, these are driven by nutrients, which are upwell from depth. Okay, and the dependence here. So there's surface winds blowing water offshore, and warmer water is moving, colder water is moving up from depths to replace that. And this general pattern is produced by high pressure atmospheric cells, which tend to be on the western side of the Pacific Ocean. Well, there's a oscillation, ENSO, the pattern of a weather pattern, or climate pattern, which periodically allows this high pressure center to move from the western edge of the western side of the Pacific Ocean towards the central side of the Pacific Ocean. And when this occurs, the trade winds tend to weaken. And with the weakening trade winds, the upwelling tends to decrease. And so this pattern of ENSO, let's see, so the El Nino Southern Oscillation is a cycle of warm and cold temperatures, as measured by sea surface temperatures in the tropical and central eastern Pacific Ocean. When El Nino is accompanied by high air pressure in the western Pacific and low air pressure in the eastern Pacific. This is El Nino conditions. You have this high pressure centered here. There's a weakening of the trade winds and a general decline in upwelling. And there are also many other climate effects or weather effects that occur as a result of El Nino conditions. And El Nino conditions typically produce mild hurricane seasons, for example, warm water patterns. So warm water tends to penetrate farther north, and along California. You get during El Nino years, you'll find fish and other marine organisms that are typically confined to the south will tend to move further north. And so this pattern, typically ENSO cycle oscillation, takes about a year. So an El Nino will be in effect for 8 to 14 months, typically. And then there's a cool phase called La Nina, when the weather pattern moves further to the east. And so we're now in a La Nina condition. And La Nina produces high sea surface temperatures in the eastern Pacific, below average air pressures in the eastern, and low in the western Pacific. This ENSO cycle, the El Nino and La Nina, cause global changes in both temperature and rainfall. And so one of the things that's intensifying our storms and everything is that we're now in a La Nina phase of this El Nino Southern Ocean oscillation, ENSO. Questions about that? So
does the La Nina event, does that influence the polar jet stream?
Yeah, tends to. It tends to weaken the flow and allow this jet stream to meander more steeply. So here's a long-term cycle of La Nina and El Nino weather patterns from 1950 to 2010. So a 60-year record, and this sort of shows you this oscillation. And the oscillation is not, it's not sort of regular, and it's very difficult to predict. One of our professors, Alan Clark here at FSU is a physical oceanographer, and he's made his career around predicting and trying to understand how El Nino and Enzo were going to vary. But here you can see, these green temperatures represent La Nina conditions, and then the warm temperatures represent El Nino conditions. So this oscillation between La Nina and El Nino are, pretty typical. And you can see that that these conditions last for a year or more. And there was a pronounced period of La Nina here in around 1973. So there had been a long El La Nina effect, and then we had a strong El Nino year in 1973. And that strong El Nino year in 1973 had the result of basically stopping upwelling off the coast of Peru. And with the end of upwelling, or the temporary end of upwelling off the coast of Peru, the populations of plankton and fish crashed. And this was sort of a new experience, and people hadn't really measured this before. And we'll talk about this again when we talk about fisheries and fisheries management, but I'll just bring to your attention this strong El Nino pattern. And the El Nino pattern occurred again in 1984, more or less. And we had another one in very strong El Nino in the late 1990s. And then more recently, the El Nino, La Nina, amplitudes have tended to decrease. Okay, where are we? So, these current patterns, high pressure air, low pressure air, the effect of this massive motion of ocean waters tends to distribute heat. And the warm ocean currents are bringing heat from the equatorial regions, from the low latitude to the higher regions. And, the opposite occurs in the return flow. So this is the Humboldt current flowing south, and the Gulf Stream flowing north. High pressure air mass causing circulation. So if you have a high pressure air mass off the coast of California, that's going to tend to produce cold conditions. And whereas the high pressure air mass off the coast of the eastern coast of the US is going to tend to produce warm conditions. And so this fundamental difference in the orientation of high pressure circulation, high pressure cells, is one of the reasons that we have a very different climate on the east coast, on the west coast of the US from the east coast of the US. So the conditions, the climate in California, and Northern California in particular, tends to be relatively, constant, relatively, doesn't change as much. Whereas on the east coast of the US, you have a higher variation between average temperatures in the summer and the winter. I believe I showed a graph of that earlier. Okay, I just have a few more minutes left, and I'm going to skip past Langmuir cells, and Langmuir cells are sort of windrow patterns. I don't know if anybody's been offshore when there's been strong winds. If you've been sailing, you'll see this pattern of foam and debris that form parallel to the winds, and these are formed by circulating air masses, patterns of convergence and divergence that produce these Langmuir cells. So these are small scale circulation cells. Okay, so there's a bunch of different sort of more regional scale processes that are significant on a global basis and produce very different conditions regionally. There's another topic that we need to talk about, and that's this concept of thermohaline circulation. So until now, we've been talking about the pattern of surface currents occurring essentially in the upper 100 to 200 meters of the water column, where the wind is the principal driver in the motion of water. Well, when you get below and most of the ocean, you know, sort of 80% of the ocean volume is below that surface area. So there's this huge mass of water that is relatively unaffected, at least directly, by wind patterns. Nonetheless, this deep water is in motion, and that motion produces long-term global climate effects. And this process generally is called thermohaline circulation. So thermohaline circulation is generated not by friction of wind blowing across the surface, but by density differences in water masses. So we have the surface water to about 200 meters, and then there are different other regions. The central waters, this is to the bottom of the main thermocline, intermediate water down to about 1,500 meters, and then deep water. So from about 1,500 meters down to about 4,000 meters. And then finally bottom water, which is water in contact with the seafloor. So these are the major water masses by depth within the ocean: surface water, central water, intermediate water, and deep water, and then finally bottom waters. Okay. Well, a couple of things are happening as you go from the surface to the depths. One thing is that it's getting a lot colder, right? And the bottom water of the ocean is where the ocean water has its maximum density. And most of the deep water and bottom water temperatures are around 2 degrees Celsius, so very cold, colder than most soft drinks. 2 degrees is really pretty cold. The thermohaline and the surface flow typically are connected. Polar regions is formation of bottom water, downwelling, and then water masses that move across the ocean bottom, across the ocean bottom and slowly rise. So these are the major components of this thermohaline flow that we're talking about. Polar regions, water masses moving slowly across the ocean bottom, and then eventually rising, convergent zones, and currents that are flowing. So how are these things generated? Well, let's look first at the formation of deep water in the Antarctic. So if we consider the Antarctic region, we've got air temperatures that are around 0 degrees C. And of course, salt water freezes at a lower temperature than fresh water. So at about minus 1 degree C, we start to get the formation of sea ice. And this is depicted as, in this cartoon, this formation of sea ice is depicted as formation of an iceberg. In fact, the formation would be, surface, ice that's forming. But let's bear with me here as we go through this. All right, so at 1 degree, we get the beginning of formation of sea ice. Okay, what do we know about sea ice? As we talked about in previous lectures, sea ice is entirely fresh. So when sea ice forms, it removes fresh water from the surrounding water and leaves behind its dissolved solids. So water around, to form this, the fresh water, concentrated fresh water in the ice, you have to produce higher concentrations or higher salinities in the surrounding water. So as the mass of ice increases, air temperatures are decreasing further, eventually you get a very large mass of ice that's formed. Well, the surrounding waters then are, relative to the fresh water in the ice, are saltier, and they're saltier than the water further away from where the ice is freezing. So there's a increase as there's low temperature, high salinity water, and that low temperature, high salinity water is going to start to sink. And so you can, by freezing ice in polar regions, you can generate a flow of a downward flow, a downwelling of relatively salty water. And that's what occurs in the Antarctic regions. So the Antarctic deep water forms when freezing sea ice drives off salt, making brine. And these dense brines sink down and they mix with North Atlantic deep water to form super dense salt water, which then circulates around the South Pole. So the densest water in the ocean anywhere is water which is salty because of extruded salts from the formation of sea ice, and very cold because these conditions are very cold. And so there's a circumpolar flow of very cold Antarctic bottom water. So if I asked on an exam, what is the densest water in the ocean? The correct answer would be Antarctic deep water. But we're talking about another type of water here, North Atlantic deep water. And we want to think about another way that we could form deep water, that we could make water sink. Well, let's recall that this diagram, which you had on your homework 2 weeks ago. And we said that ocean water can be classified by temperature and salinity. And when water of different density but different temperature or salinity mix, the resulting water is denser than either of the parent waters. And so you get this effect called caballing, and that causes water to sink. Well, you probably remember this is sort of an abstract concept from our homework, but that's in fact what happens in the North Atlantic, in the Weddell, in the Norwegian Sea and the Labrador Sea. So, you know, what's going on in this region here is you have equatorial region surface flow. So there's warm saline water mixing with cold, relatively fresh water. So in the North Pole, the formation of deep water is not so much caused by the freezing of sea ice as it is by the melting of sea ice in the presence of very cold water. So you have relatively warm, salty water mixing with much colder, relatively fresh water. And so the combination of those two, when you combine these two of similar densities, but different temperature and salinity regimes, you get this sinking effect. And so this sinking effect is what is responsible for most of the formation of deep water. So deep water is forming in the North Atlantic, where there are regions. So this is where, so what you see is you have high saline water, relatively salty water, a lot of it coming from the Mediterranean, moving northward and mixing with this colder water. And water from the Arctic Ocean mixes with the salty Gulf Stream water and salty water from the Mediterranean, and the resulting deep water mixes and flows southward.
So we can get a picture of that if we look at the density structure of the Atlantic Ocean. Okay, once again, we're looking here at a profile through the ocean from the southern latitude all the way up to northern latitudes. This goes down the middle of the Atlantic Ocean, and you can see the bottom represented here. And you can see there's an abrupt decrease in depth as this profile crosses the mid-ocean ridge and passes right by, I guess, Cape Verde Island or something like that. So it looks like there's actually a very shallow portion of the ocean. But most of the ocean is quite deep. The average depth along this line can be about 4,000 meters. And then here, as we get far north, we start to approach the Greenland, the coast of Greenland. Okay, so what's happening in this? We've got these different abbreviations: NABW, AIW, ABW, MOW. What do these things stand for? Well, I've been talking all along about how different water bodies can have different temperature, salinity, different density characteristics. And I've also sort of indicated and hinted that these bodies don't tend to mix. These water bodies don't tend to mix very well with each other. So once these bodies form, their temperature and salinity characteristics tend to be preserved. And so here's a body of water. This AIW stands for Antarctic Intermediate Water. And this is water that's cooling off in the near the coast of Antarctica. And because it's so much colder, it's sinking under this warmer, more saline water. Remember that we saw high salinities in the surface waters to the south of the equator. So here's the equator, here's this high saline water. So this is cold water from Antarctica sinking underneath and flowing northward in this surface layer. On the other side of the equator, we have mid-ocean water, MOW, also sometimes called mid-Atlantic water. And this is characterized by relatively high temperatures and relatively high salinities. And so the salinities here can get as high as 36 or 37, and the temperatures are relatively low. Okay, well, what's happening right up here is that this high salinity, relatively warm water is mixing with water that comes down from the Arctic Ocean, down in through here. And this water is relatively fresh, has low salinity, partly because it contains meltwater from the Arctic ice cap, but it's quite cold because it's coming down from the Arctic. Okay, so here you have high salinity, high temperature water, higher temperature, warmer water, mixing with low salinity, low temperature water. So when these two waters of constant density are mixing together, you get water which is denser than either of the parent bodies. And this water sinks down and forms what's called North Atlantic deep water. And this North Atlantic deep water flows southward. And this is the beginning of a feature.
So this is the feature that flows around. Okay, so let me just finish here. We've got just a bit left. So of course, the deep ocean, has got different patterns to it. Let's see. So these are the patterns of upwelling and downwelling across the major ocean basins. So there's deep water formation here, here, here. And then there's upwelling zones, and I talked about the equatorial upwelling zone. There's an upwelling zone off California, and there's another very important one off Chile and Peru. And these are the sort of the major rising and sinking patterns globally. And all of this gives rise to something called the ocean conveyor belt. And I'll just close with letting this video show go forward, and you'll see how these current patterns work globally. There's a north flowing water flowing the surface, being entrained to the Gulf Stream, moving up, mixing with this cold, fresh water, sinking down, and then flowing southward in the North Atlantic deep water, or the region. So this formation of North Atlantic deep water is extremely important. This is where most of the deep water formation is occurring in the Atlantic. And so this depends on the ability of cold temperatures in the Arctic. And so then this water flows down, it flows at an intermediate depth, it mixes with the Antarctic deep water, continues flowing around. There's a major gyre here in the eastern Indian Ocean. Another western intensified gyre. Water is flowing around, continuing. There's water entrained here. And this conveyor belt. This was first described, or most famously described by Wally Broecker, who was one of the great oceanographers of the 20th century. And this global pattern of circulation pattern then, describes this major motion of water. And this, what it's producing is something called the AMOC, Atlantic Meridional Overturning Circulation. And so that's the formation of cold water here, and the tendency of the North Atlantic or the Atlantic Ocean to mix across sort of 100-year timescales. And oceanographers are concerned with this warming of the Arctic, because with the warming of the Arctic, the tendencies, the processes that would produce this North Atlantic deep water formation might be weakened. And so oceanographers are very concerned now with trying to measure the strength of this overturning circulation. And people are saying that the Gulf Stream may be slowing, that there may be less deep water formation, and we don't know that for sure. But if that were the case, there would be major impacts on global climate conditions. Okay, well, I've run out of time and I've run over time a little bit. It's hard for me to keep exactly on time with these Zoom classes. I hope that doesn't cause too much disruption in your schedules. But I will end today's lecture. And if there are any questions, I'll be happy to answer questions. If you want to email, and then we'll look for your milestone 2 grades over the weekend, and we'll be having conferences next week to make sure that if you have a chance, if your team needs to revise, that you have a chance to revise that. Okay, any questions before we close? Questions? Let's see, some questions in the chat. Let's see. Okay, well, I don't see any questions, so I will stop sharing. And okay, well, goodbye, everybody. Have a good weekend. Hope the weather cooperates, and hopefully we won't get too much of this strange weather pattern down here in Florida. I think, though, it kind of shows us that it could happen here. So, even though we're used to we've kind of dodged the bullet in terms of this current pattern, I'm concerned that we could get this same sort of winter storm impact here in North Florida. Probably not this time around, but at some time in the future. So if you don't like the weather, hang on. Okay, have a good weekend, everybody. Goodbye now.